suggestions and some examples for calculus optimization questions. So calculus optimization questions are really just like min and max questions, but they're an application problem, so something real world related. So as we go through these questions, anytime you can make a sketch, that's a good idea. Assign symbols to stuff that you know and stuff that you want to know. Sometimes we might talk about a primary equation. That would be the thing that you want to maximize or minimize. So like if it was about a business and it was profits, you're probably going to want to maximize that. And if it's cost, you would probably want to minimize that. But we will need to use a little bit of calculus here, so it certainly helps if we get it down to a single independent variable instead of multiple. So sometimes we get some more information so that we can do that. We should think about the domain of the primary equation. So if we work it out and the algebra or calculus says we've got multiple answers, it could be that maybe only one of the answers even makes sense. And of course we can use calculus to determine min and max values. So first derivative test and second derivative test, both are good for finding local min and maxes. Alright, so question number 1, as an example here, find the length and width of a rectangle that has a perimeter of 100 meters and a maximum area. Alright, so my first clue said make a sketch if you can. So here's my rectangle, length and width, and I'm trying to maximize area. So that's what we might refer to as our primary equation. Well, based on the shape, the area is going to be length times width. And so I guess you could come in here and say, all right, well, I'll try to maximize this, so let me take the derivative. But if you do it already, then you've got L's and W's, and you're going to have to do the product rule, which is fine, but you may not have all the information that you need to plug in to maximize the area here. So before we take derivatives, this clue says let's try to get it down to a single independent variable. So L's and W's, there's 2 independent variables there. So this other clue says that the perimeter is 100 meters. Well, perimeter, 2 lengths, 2 widths, and we've got 100 feet to go here. So this allows me to solve it for L or W. Okay, so it looks like the width is 50 minus L. And then if we go and plug that into the primary equation, we can now say area for this particular problem is length times 50 minus length, or 50L minus L squared. Okay, so now I just want to maximize this. I want the maximum area. So I'm going to think of this like I did with the first derivative test. I want to find the critical numbers, test around there, so I know when the graph's increasing and decreasing, and the max is going to be when it switches from increasing to decreasing. So take the derivative. Critical numbers would be when this is undefined or equal to 0. Doesn't look like it's going to be undefined, but it looks like it's going to be equal to 0 at 25. So 25 is a critical number. Now we got to be careful here. Just because it's a critical number doesn't guarantee that it's a max or a min. It probably is going to be the maximum value here because I don't have many other options. But we should still go ahead and test around it. So maybe test 30 into the first derivative, and that would be a negative number, so decreasing. And maybe test 10 into the first derivative, that would be a positive number. And the first derivative is positive, is increasing. And now I can see that when L is 25, when the length is 20 25 meters. That's what's going to give me a max. And now that I know the length, I could plug that in, I guess, basically anywhere. That would then solve for W. So 50 minus 25 gives me width. So width is 25 also. So under those conditions, if you want the max area, you really just want it to be a square. So there we go. So if we kind of recap what those suggestions said, you can see all of those are pretty helpful. We got a picture. We found the equation we were trying to find the max or min to. We used some of this other information so that we could then plug it in to the primary equation and get it down to a single variable. So I got it down to just L's. And then I can maximize it with the first derivative test. So find the critical numbers by finding the first derivative, figure out where they're 0 or undefined, and then plug in numbers in the first derivative around there, and then you know the shape of the graph was going up before 25 and down after 25, which meant 25 was a max, and that allowed us to get our answer. Okay, so let's look at one more example here, and then that will be it for your video here. We'll spend some of the class period working these together as well, but I would like you to try one after number 2. So I'm going to do number 2 for you now too, and then if you would just find maybe one more on this worksheet to go through and try, that would be helpful. Alright, a farmer plans to fence a rectangular pasture adjacent to a river. So we've got this, but over here, this is a river. It must contain 180,000 square meters in order to have enough grass for the herd. What dimensions would be required to have the least amount of fencing if no fencing is needed along the river? Alright, so we're not worried about our animals trying to cross the river, so we get away with having that side not fenced in. And so this time it sounds like we need to try to minimize the amount of fencing. So in this case, I call this length. This would be my width. So for this particular question, my perimeter is 2 lengths and 1 width. And this is going to be the primary equation, because this is what I'm going to try to minimize. Okay, so I could take derivative at this point, but I've got 2 independent variables, and so that's going to be problematic for me. I don't want to deal with that just yet. So I'm going to use this other information that I want the area, which would be length times width. I want it to be 18,000. Or 18,000, 180,000. So I could use that to maybe solve for W or L, take your pick. W would be 180,000 over L, and then I could go and plug that in up here to make my primary equation only have L's in it. I'm going to move that up as a negative exponent, and now I've got the primary equation down to 1 variable, and that's what I want to minimize. So now it's not just some random function that has no real life context to it. Got a real reason why we might want to solve this. So I know the min is going to occur at a critical number, and critical numbers are when the first derivative is 0 or undefined. So take the derivative, maybe rewrite it. I would probably also make it have a common denominator here. So let's multiply the bottom by L squared and the numerator by L squared. So that we can get a common denominator. And that just makes it a little bit easier for me to solve for. Because a fraction is going to equal 0 when the numerator equals 0, that's going to be some critical numbers, and when it's undefined. So that's when the denominator equals 0. So it looks like we're going to have critical numbers for sure at 0, because L equals 0 here. And I don't know, to solve this one, I'm going to need a couple steps. And then square root. Normally when you take the square root of both sides, you need plus or minus, but this is a length, and of course negative length doesn't make sense. So thinking about the context of the question, let's see, 300 times 300 would be 90,000. So it looks like the other critical number is 300. These are my critical numbers. So they might be maxes or mins or neither. Okay, so I guess I could test around this critical number, but it doesn't make sense to test over here, because if the length is negative, then that's not even going to be possible. So this is one of the rare cases where I don't really even care what's going on over there. It doesn't even exist. But I could plug in anything here. So I'm going to pick 1 because that sounds really easy. Plug it into the first derivative, and I would get a negative over a positive. So that would be negative. And then I will test over here, like maybe 301. And so this would be positive because this is squared. This would be positive, and if I squared that, that would be slightly more than 90,000. Times it by 2 would be slightly more than 180,000. So this would be positive. So positive over positive means that the first derivative is positive and increasing. So now I can visually see was decreasing, then it's increasing. So this is going to be a relative min. So that's good because that's what I wanted. I was trying to find the least amount of fencing. And so that would be when we have a length of 300 meters, and once I know that, the width shouldn't be a problem. I can plug that into any one of these equations, like maybe up here. If the length was 300, then we would want the width to be I guess I'll plug it in here. The width would be 180,000 divided by 300, which would be 600. Okay, so it's kind of like question 1, except that we don't have 4 sides, so we got a little bit of a curveball there. But we need to see that all the same steps were helpful, because each one of these questions is of course going to be different, but the approach should still be good. Picture helps. Think about the formula you're trying to maximize or minimize the primary equation. Use your other information so that you can get your primary equation down to a single variable. Find the critical numbers by finding the first derivative, setting it equal to 0 and undefined to know where the critical numbers are and where you might be having a max or min. And then you can apply the first derivative test to actually see when your function is decreasing and increasing, and then you should be able to visually see the information that you're looking for. Alright, so that's all for this one. So again, if you just kind of scan the rest of the questions and just find maybe one of those that looks interesting to you, and give that one a shot before you guys come to class next week.